Hello, and we're going to discuss, that's the word, acceleration. And if you recall, velocity told us how quickly your position is changing, or some object's position is changing. And acceleration, in turn, tells us how quickly your velocity is changing. And average acceleration has this definition right here. Okay. And again, the delta v and delta t, you're looking at final velocity minus initial velocity, always final minus initial. And one thing I neglected to do when we talked about velocity is talk about the units that are implied by its definition. So I'll make sure to do that here with acceleration, and we'll get to the velocity units along the way. All right. So if we look at this definition, delta v, or any of the velocities in delta v, well, remember that's a displacement over a time. So in standard units, that's meters over seconds, which we usually abbreviate as just m over s, okay? And time has units, standard units of seconds. All right. So when we're looking at the units of acceleration, which is equal to delta v over delta t, well, that's meters per second, which is a little difficult to say. But you can see, right, meters per second is velocity over seconds is delta t, so our period of time. So usually this, if you do a little bit of algebra there, this is usually said as meters per second squared. All right? So meters per second squared is the standard unit of acceleration. Okay, so acceleration, again, tells us how quickly velocity is changing. It doesn't really tell us anything about, at least nothing directly, about the value of the velocity at any particular moment. It just tells us how quickly that velocity can be changing. And if you think about getting started from a stop sign in your car, if you hit the gas quite abruptly and you wait a tenth of a second, well, not much will have happened with your velocity. I mean, you'll have increased from zero velocity at the stop sign to some forward velocity. But the thing that's actually quite big at that moment is acceleration, because you're changing your velocity quickly. So if you keep the gas pedal down, you'll eventually have a very large velocity. Okay. Now, let's look at a special case for acceleration, and one that will come up quite often for us. And that is the case of a constant acceleration. And what we're looking at here is a graph of acceleration versus time. And you can see that the line here going across, okay, doesn't change, right? If you look at the value at this moment in time, and this moment in time, and this moment in time, and this moment in time, the value of acceleration is always the same for all time. That's what we mean by constant acceleration. So there's our acceleration, there's our time. Now, if we look at the corresponding graph of, whatever object this is, thinking about its velocity, well, if we assume that it starts at zero velocity, and say we're talking about that car moving away from the stop sign, we hold our foot on the gas pedal at a constant pressure, so we have a more or less constant acceleration. And if we look at that graph, we've got something that looks like this. Now, it's important to realize that just like the velocity is the slope of a position versus time graph, acceleration is the slope of a velocity versus time graph. We can see that in another way, okay, rather than just stating it, by looking at the definition of average acceleration, which if we multiply both sides by delta t, we get this on one side, and we get delta v on the other side, okay? That's a little awkwardly drawn, okay? But our velocities, right, on our graph are on the y-axis. Our t's in our delta t are on the x-axis. And so if you remember back to Math 100 or whatever prerequisite math course you took to come in here to this course, then this looks like the equation of a line where the average acceleration is m, or the slope of that line, okay? So it turns out this is generally true, okay, that the acceleration is the slope of the velocity. And you note that the acceleration is positive here, some value, and so that corresponds to a positive slope at that point on the velocity graph. And the slope of this graph is not going to change because any point you might want to pick on the acceleration graph, okay, is always the same value, so the slope of the velocity graph better never change if this definition is true, and it is, okay? Now, if we then look at the corresponding position versus time graph for, say, our constantly accelerating car, well, it looks like this. Now, let's think about that for a moment. It's not a straight line, right? The slope starts, so small slope down here. That's slope, there we go. And higher slope up here. And this whole thing, you can imagine, just sort of keep on going up like that. Now, why is that? Well, remember that velocity is the slope of an x, so position versus time graph. And so down here at, time 0, or close to it, well, the value of the velocity is small and positive. So when we come down here to the x versus t graph, well, the value of that slope is going to be small and positive. And when we come up here to the other end of the graph, well, our velocity is significantly larger. And so the slope of our x versus t graph is going to be significantly larger. Now, just thinking about why we would have, stepping back from the definitions for a moment, why we would have this constantly increasing slope, this position that changes faster and faster and faster and faster as time goes by. Well, if we have a constant velocity, well, then we're going to cover exactly the same amount of ground in a certain period of time, 1 second, every second that goes by, right? So if we're going 10 meters per second in terms of our velocity, well, then every second that goes by, we are covering 10 meters. And so the shape of our x versus t graph would just be a nice constant linear thing, kind of like our velocity graph looks like on this diagram, all right? Because our velocity is constantly increasing, well, every second that goes by, we're covering more ground in that second. And so the sort of rise over run, the amount that we go up on the graph for going over, say, 1 second here, well, we've gained, this much position. We go over another second, and we've gained much more position proportionally in that same second. We go over another second, and again, we've gained a lot more x proportionally in that third second in the whole sequence, okay? So if you're accelerating, you're increasing your velocity as you are here with a positive acceleration and moving in the positive direction, then your x versus t graph has to have this parabolic shape, okay? As it will turn out in our equations of motion, we'll see this relationship between the position of an object and time being related to t squared. So that basic equation for a parabola on a graph. So I think that's all I'd like to say about acceleration for now. We'll come circling back around to these quantities a lot over the next few mini lectures, but we'll leave it there. Thanks for listening, and I hope this came out well.